go. All right, good morning, everyone. So today, we spent last time working out what the Einstein equation should be and what its meaning was. Today, we're actually going to try to solve the Einstein equation. And I'm going to show you some techniques for doing that. Starting with the Schwarzschild solution, which we've already seen in Eric's lectures, discussed in great depth. But where does that come from and how do you get it? How many of you have ever worked out the Schwarzschild solution from scratch? Okay, more than I expected, so that's actually good. Uh, it's it's a long and tedious calculation, although considering the fact that Schwarzschild himself worked it out in the trenches of World War I, in between battles, it's not as bad as it could be. But I'm going to show you a way, and we ought to be able to do it. We're in a much nicer setting, but I'm going to show you a way that you can actually make that calculation fairly directly. And in fact, you can use the same method to generate the other coordinate systems that Eric was showing us. You just adjust certain parts of the derivation. So we'll do the Schwarzschild solution. And I want to spend a little time, I'm trying to decide exactly how much, but to spend a little time on interpreting the Schwarzschild solution because it's a good lesson that coordinate names actually mean nothing. So I want to work on that. But we're all interested in gravitational waves, and the path to understanding gravitational waves is through the weak field approximation, where I'll also discuss the phenomenon of gravitomagnetism, and I'm going to show you something very powerful there too that I think you'll find useful and isn't in a lot of textbooks. And then we'll talk about gauge freedom, which is going to be a big issue when we talk about gravitational waves. So, we solve the Einstein equation. How do you solve a set of 10 coupled nonlinear differential equations? Well, you solve it like you solve any set of differential equations. You guess, right? You guess a solution, you use symmetry, you use whatever you can put together. Put together a reasonable solution, plug it in, solve for a few undetermined parameters. If you can't get a coherent solution, then you start over with another guess. That's what we do. That's the only way to do it. So we're going to assume two basic symmetries. We're going to assume spherical symmetry, which means that I can imagine putting around my source a set of spheres, spherical surfaces, imaginary spherical surfaces, and that will reflect the symmetry of the source. And I'm going to also assume time independence. And I should be careful about saying static here, but yeah, I'm going to assume the star is static for the purposes of it's at least stationary. All right, and we want to solve the empty space Einstein equation, which means that all the complicated stress energy stuff is zero, and that's why it's nice to have the equation in the form where r mu nu is on one side, the Ricci tensor is on one side. It works great in vacuum. You put all the complexity on the stress energy side, and then you set the stress energy to zero, and all that complexity goes away. And we're going to do this in the vacuum region outside the star. So that's where the stress energy is zero. So if you have spherical symmetry, then you can imagine surrounding the star with nested spheres, And spherical symmetry implies that we ought to be able to use ordinary spherical type coordinates. And the metric for a spherical coordinate basis, we derived ourselves a few sessions ago. That's what it is. So we're going to use theta and phi coordinates, and they're going to mean the same kinds of things that they usually mean on those surfaces. And this implicitly defines what we mean by this thing. We're calling it R, but what does R mean? Well, it says that the arc length of an equatorial circle around one of those spherical surfaces, if you do, I'm going to take theta equal pi over 2, so I'm in the equatorial plane. I'm going to take d theta equals 0. I'm going to take dt equals 0. I'm going to take dr equals 0. I'm just going to integrate around using the metric. I get 2 pi r. And so my r coordinate is a circumferential coordinate. If you measure the circumference of the circle, divide by 2 pi, that's what you say r is. Now, in ordinary Euclidean geometry, that would be the same as radius. In Schwarzschild geometry, it's not the same as radius. R is not a radial coordinate. But the metric makes it clear that it is the circumferential coordinate. Okay? And then you can, so I can put these coordinates on each sphere, but how do I make the spheres, the coordinates line up? Well, I choose radial lines, and I can certainly define radial lines in a spherically symmetric space. And I connect all the coordinates together on all my nested spheres by making them all equal along a radial line. And that way I align all the spheres so that the coordinates agree with each other, and I ought to be free to be able to do that. So then my basis vectors are all mutually perpendicular in that kind of situation. Does that make sense so far? So, but all I'm doing is trying to guess what a basic solution might look like. All right? So our metric so far looks like this. I don't know what this is, but I know on the sphere it ought to look like that. And this is just the spatial part of the metric. So what other terms might I have? Well, I know that I've got no off-diagonal spatial terms, but might I have a term like this, where I've got an off-diagonal angular term? Well, that would kind of imply that there's something physically different about going in the plus phi direction and forward in time, or the minus phi direction and forward in time. And that doesn't seem consistent with spherical symmetry, or time reversal symmetry for that matter. So I don't think I want to include a term like this. It doesn't reflect the symmetry that I want. And an off-diagonal term like this would also violate time reversal symmetry. So we ought to be able to find a solution of this form where I have no off-diagonal component. Anyway, that's a good guess. We don't have to choose this to be 0, but we ought to be able to choose it to be 0. And in fact, we can, as it turns out. So, and moreover, the spherical symmetry and time independence suggests that none of these components should depend on theta or phi or t, so they ought to depend only on r. And that's actually, most of the work is done now because you've made a guess based on the physical situation, an educated guess about what the solution would be. We've only got 2 unknown parameters to solve for, and they just depend on one coordinate. All right, so let's go. Now the tool, yes.
I sort of get some of that logic.
Uh-huh.
You don't
Yeah. Yeah. Well, the good question, and but again, that would sort of suggest that going in the minus, if you have an off diagonal term, it's one thing to have theta dependence in the spherical part, and we saw where that came from when we were doing the analysis, because we're doing circles of latitude, and they don't have radius r, but they have radius r sine theta. So yeah, it makes sense in that kind of a context, but we certainly don't want off diagonal terms involving theta. And then, yeah, but your question is maybe the diagonal terms could depend on theta. So let's try a solution where they don't and see if we get something. If they must depend on theta for some reason, which is certainly not obvious from the geometry, then we'll know because we won't be able to find a solution. And then we'll go back and do something more complicated. That would be my way of talking about it. So there are a whole bunch. Yes, question. Yep. Yes, you are absolutely right. And so any function of r would totally work. What I'm doing here is actually defining the r coordinate. I could call that coordinate anything I want. I could assign it any function I want, but I am assigning it before I even try for the solution. I'm assigning it a particular meaning. So this part of the metric defines the coordinates actually r, theta, and phi. They are now defined. We don't know yet what the t coordinate means. We don't really know what the how the r coordinate is going to relate to radial, but we do now know what that coordinate means. So I could make another definition of it. It would yield a different solution, a different way of labeling the same geometry. So absolutely. Other questions? Okay, so how are we going to do this? Well, there are lots of different ways to do this. You can grind out everything by hand. We've got the definitions of what the Ricci tensor is and Christoffel symbols, and you can do that all. And that's a lot of work, but that's what Schwarzschild did, so it's possible. The other way is that you could use a tool like Sage that Eric has been talking about, which is a very powerful tool in some regards, but I gotta say it looks like a pretty high learning curve. And it was a little too tough a learning curve to either learn mathematics or a Sage for the students in my undergraduate class. So I developed a different kind of technique because I wanted them to be able to do this kind of calculation without the high learning curve. So it's a really kind of a low-tech solution, but a useful solution, and that is something I call the diagonal metric worksheet. So if you have a diagonal metric, A, B, C, D, these A, B, C, D can depend on any coordinates, and I'm just numbering them 0 through 3. I don't care what the names are. And the metric works, the diagonal metric worksheet, in fact, I'll show you what that looks like because you can access it on the Les Houches, my Les Houches website. Go to the diagonal metric worksheet, click on it, it comes up, there it is. Okay? And so given a diagonal metric, and I'm using a shorthand notation to make things a lot clearer. So a sub 0 is the derivative of a with respect to coordinate 0. And you can get all the Christoffel symbols and all the Ricci tensor components It's all written out there, what they all are. Okay? And so, how do you use this? Let me show you. Whoops, I want to go back into Keynote here. And so the way I would do it in this particular case is that I know what C and D are. It's r squared and r squared sine squared theta. And I know that A and B only depend on r. So I go through this thing term by term and I rewrite what they are in hand, and then I can't cross out anything that's 0. Why is this 0? Yeah, it doesn't depend. A doesn't depend on theta. A doesn't depend on phi, etc., etc. And so I write all the terms that are actually not 0 and cancel all the other terms, and then at the bottom I just gather the terms that I've got. And so that's the r sub tt component of the Ricci tensor. And so you can do that kind of thing very easily. And it turns out that the RTT component, I've just written it there, rewritten it there. The RR component is similar. The R theta theta component is different. And then the R phi phi component is pretty much the same as the R theta theta component. You just multiply by sine squared theta. And everything else is 0, identically. Okay? And that's actually, it doesn't take very long at all to do this. Longer than we have right here, but it doesn't really take very long to do that. Now, I've got 3 coupled equations and the 2 unknowns that I have. I certainly ought to be able to solve. Yes? Yeah, that's a choice. And like I say, if that choice turns out to be bad, then I won't be able to find a solution. And then I'll go back and say, well, gee, maybe it did depend on theta, and I'll try that. Okay? So the way to solve a set of equations like this is the usual way that you solve a set of equations. You try and simplify and eliminate, add, subtract equations until you get some things that you want. Remember that all these have got to equal 0. So I'm going to take this equation and multiply it by b to get, in fact, 2b to get rid of this factor out in front. I'm going to multiply this by 2a to get rid of that factor. And then you see that a lot of terms are going to cancel out except for this one. And so you end up with, no, this one cancels out. It's these 2 that don't cancel out when you add them. And so this contains some useful information, and I can rearrange that equation by multiplying by both sides by r, and it looks like I'm multiplying by BA, and then you get an expression like that, and you see that that's the same as the r derivative of that. So what this is saying is that A times B is some kind of constant. Now, what constant? Well, it's arbitrary. You choose whatever constant you like. But there is a choice that makes things nice, and that is if you have flat space at infinity, then your GTT ought to be 1. It ought to be minus 1. And your GRR ought to be 1. And so the ratio at infinity would be 1. if you're going to reduce to the flat space metric. So let's make that a requirement. Yeah, we want to reduce to the flat space metric, in which case, what is AB? Yeah, it's -1. Okay, so we're gonna assume that. Actually, the minus is outside the A, so the A is just the part. The minus is already built in, so the AB is equal to 1 in this case. Okay, so now we're going to substitute. We know that B is equal to 1 over A, and we can take the other equation that we had from before, and we can plug it into the third equation and eliminate all references to B. And you get this simple equation that 0, r theta theta's got to be equal to 0, and I've eliminated references to B. And so I'm going to move the 1 around and shuffle things a little bit. And I get that. And you can see that that's equal to this. And so what did I do in going to here then? So going from this expression to this expression, yeah, I just integrated. I've got a constant of integration that comes there. And so I can solve this for A. A is equal to that. Okay? And then you choose your constant of integration to fit your conditions. Where you can see by calculating the Christoffel-Simpson acceleration and matching with Newtonian prediction that if k is equal to 2gm, then we get the Newtonian result at distant r. And so that's what we'll choose the constant to be. So A is equal to this, and B is 1 over A. We've done it. We've got it. And it's not that bad. It's not that bad at all. So now we've got the complete metric. So I want to talk a little bit about interpretation of the metric. And by way of doing that, emphasize a really important truth that I'm going to emphasize over and over and over. And I want you to, if you come away with one thing, this is what I'd like you to come away with. The coordinates by themselves mean nothing. I could call these coordinates A, B, C, D. I could call them Q, X, N, W. And they would exactly have the same meaning as TR theta phi. We think that we know what TR theta phi means, but you never really know what the coordinates mean unless you go to the metric. Okay, well, we've already talked about what the r coordinate means in terms of being a circumferential coordinate. You take one of your spheres of symmetry, you measure the coordinate, you measure the circumference around the equator, you divide by 2 pi, that is your r coordinate. And that's what the metric says the r coordinate is. That's a definition. But it's not a radial coordinate. And the reason that it's not a radial coordinate is that if I take a purely radial curve, time equals 0, theta equals 0, phi equals 0, or I mean dt equals 0, d theta equals 0, d phi equals 0. So a purely radial curve, the metric tells me that the distance between a sphere with coordinate r0 and a sphere with coordinate r1 is this. Kind of ugly, nasty, but Wolfram alpha can handle that. So that's not equal to r1 minus r0. So our coordinate here is not a radial coordinate. And t is not what a clock at rest measures. And so you do the same kind of thing. You say dr is equal to 0, d theta is equal to 0, d phi equals 0, and then you do the time that a clock at rest would measure, and you get this. So the clock at rest actually is running slower than the t coordinate. And those two will agree only where? At infinity, yeah. So clocks at rest at infinity read coordinate time t, but clocks down in the gravitational field don't. And the other thing I want to show is that, again, from the metric, and Eric did this yesterday, here is the equation for how light flashes move in terms of radius and coordinate time. And the main thing I want to get at in this particular context is that in the Schwarzschild coordinate system, the way we've set it up, the metric says that the time going out is the same as the time going in. That the speed, it doesn't matter whether you're going out or in, the speed of your light flash is the same. Okay? And that's actually an implicit statement about clock synchronization, what you're how you're defining your synchronizing clocks. So if I imagine, and so now this gives us enough information to imagine constructing a machine that will measure Schwarzschild coordinates. All right? And this is the kind of thing you have to really go through with almost any coordinate system you have, is what does the metric say about how to construct a machine to measure those coordinates? And if you don't know how to construct the machine, you really don't know how to work the coordinates. So, all right, let's imagine setting up a lattice around the star with a bunch of spherical surfaces. And so I construct big spherical surfaces, and I can tell if I'm spherically centered on it because of the spherical symmetry of the star. And then I'm going to lash them together with radial girders, and I'm going to label all the points along a radial girder to have the same angular coordinates, and I'm going to label each point on each surface by the circumference that I measure around that spherical surface, and I'm going to divide it by 2 pi, and I'm going to put a sign up there that says r equals 5,000 meters or whatever. And then I'm going to put a t meter, what I call a t meter, at every intersection, which is turned up to match the clocks at infinity. So clocks at infinity are going to send signals down into the light flashes, down into the gravitational well, 1 per second, say. And then, of course, my clock, my watch down here says, oh, they're coming faster than 1 a second because of the blue shift. That's implicit in the metric. So I'm going to turn up my t meter. I'm going to crank it up a little bit so it matches the rate at the clocks at infinity. All right? And so now I've got things that would read t time at my local position, except I don't know how to synchronize them all. And I could synchronize them in a bunch of different ways. And if you synchronize clocks in different ways, you get different solutions. That's one of your coordinate choices. But in this particular coordinate choice that we have made, light travel time down is the same as light travel time back. So what I can do is arrange with the person at infinity. Now, I'm using infinity loosely here, but I can arrange with the person at infinity. Okay, you're going to send me a signal at noon. I receive it at noon plus 1 second. I send a signal back to you. You receive it at noon plus 2 seconds, and then we know that I'm 1 second of light distance travel time from you, and so I can make sure that my clock is set appropriately. So it's the same kind of thing that we do in ordinary Lorentzian systems. We just exchange light signals to make sure that our clocks are in synchronization. Does that make sense? So this is how you would do it. But I want to say that there are different ways to synchronize clocks. A completely different way of doing this, which would lead to a different synchronization and thus not the Schwarzschild metric, would be to take the clock and drop it from infinity, and then everybody sets their clock as the dropping clock passes by. You just set it to agree with whatever that clock says. Okay, that's a different way to synchronize clocks. If you do that way, you'll get an off diagonal term in the metric, and it's a different way of slicing up space and time to construct different hypersurfaces of constant time. And there are many, many ways to do this. And one of the things that it's fun to try and do is not make, is to relax the assumptions. One of the assumptions about that to include the possibility of an off-diagonal term. And if you include that possibility, then you'll see you have a whole bunch of freedom. And you can choose different synchronization methods. Still describes the same geometry, but different coordinate systems that describe different ways of slicing up the space-time. So it's really important, like I say, the metric tells you what the coordinates mean. There's no other way to get that information. All right? Questions? Yeah.
Two aspects that you mentioned, I guess.
Yeah.
So I'm matching my clocks, which we say
Yeah.
t-meters seconds going to agree with how far away.
Right.
But then I also want everybody to be noon at some.
Yeah. Yes, that's right. And that's really important. That synchronization method basically defines the hypersurface in four-dimensional space-time that you are calling t equals 0. And there are just different ways of doing that, all perfectly valid, but you got to know what the method is. And the metric tells you implicitly what the method for synchronization is. And so that's an important thing to sort of get out that. Now, as Eric has been talking about, we get into trouble with this at r less than 2 gm, because GRR then becomes negative and GTT becomes positive. So the scheme falls apart. We can't determine radial distances anymore. If you go back and look at that formula, if you're smaller than r equal 2 gm, then already in this square root, you're running into trouble. You can't get a meaningful radial distance less than r equal 2 gm. A clock at rest at r equal 2 gm measures no time at all compared to the clock at infinity, so you can't synchronize. In fact, such a clock and such a user of that clock would have to be constructed of photons because photons are at rest. That was another one of the formulas. At r equal 2 gm, one of the solutions is you're at rest. Okay? So your whole lattice is breaking down here. This is the coordinate problem with Schwarzschild coordinates and why you want to use Eddington-Finkelstein coordinates or some other kind of coordinate system where that problem doesn't arise. We can't build this lattice anymore for Schwarzschild coordinates. And in fact, the core problem is that the r coordinate, because it's the negative one, in a diagonal metric, only in a diagonal metric, but in a diagonal metric, look for the negative coordinate, the one with the negative metric. That's your time coordinate. And GTT is now becoming positive. That's a spatial coordinate. And so r inside the Schwarzschild radius becomes a time coordinate. And the way I like to express this, but it's still the coordinate that labels spheres. So as r goes smaller and smaller, your spheres are getting smaller and smaller. You really are getting closer and closer to r equals 0. And so, but now it's a time coordinate also, and you must go to r equals 0 with the same inevitability that you must go to the future. So the way I put it to my students is that your future is r equals 0. Okay, there's no way to avoid it. Okay, so our whole lattice system breaks down, and this is a sign of the coordinate breakdown that you can only solve by going to different coordinate system. All right, any questions, further questions about that? Yeah.
Outside of the horizon here, which is given by the time coordinate, and inside
Yeah.
from R. Say I want to go inside
Yeah.
the horizon,
Yeah.
outside of for whatever reason. What defines my evolution at the moment that I'm crossing the horizon? R equals 2gm.
Yeah, well, your coordinate system is going crazy at that point, and your Schwarzschild coordinate system is going crazy at that point. And it's the same thing as going to the North Pole and saying, "Oh my gosh, what's my phi coordinate at the North Pole?" It doesn't. The question has no meaning, and and so you are switching at the event horizon from the t coordinate being a time coordinate to the r coordinate being a time coordinate. And at that moment, you've got no useful coordinate that's telling you. Now, there are good coordinate systems. The Eddington-Finkelstein coordinate system, a coordinate system that I like to use with my students, is called the global rain coordinate system, where you imagine robots dropping in from infinity along radial lines, and they all carry a clock, and they're all measuring the adjacent distance to the next robot horizontally. And you can measure the r coordinate, and you can measure a t coordinate, which is the robot clock time. And that coordinate system works perfectly all the way down to r equals 0. And you can do a complete coordinate system if you've got an infinite budget for robots dropping in from infinity. And it works just fine. And it shows it's one of, like the Eddington-Finkelstein coordinate, except it's easier to interpret, I think. But it's a perfectly meaningful coordinate system where the time coordinate in that coordinate system, which is the robot time, is always well defined, and it's always the time component. So you get into no trouble there. So if you're interested in that, you can talk to me later about it, or look in my book about that.
Discussed, I think, all external forces. So if I dangle a rope through
Yeah,
my spaceship, or if I have a spaceship with good engines.
yeah, right. Well, good. Yeah, these are good questions. And one of the ways to answer that question is you can calculate, and one of the things I have my students do in homework is calculate the acceleration of the spaceship you would need as you approach r equals 2gm. And you do that by going to a frame where the spaceship is at rest, and you calculate the forward acceleration of that, and you basically you find that the acceleration goes to infinity, okay? Which means if you were to dangle a rope, you would have to exert an infinite force on particles at the horizon in order to hold them there at the horizon. And so what's going to happen is you dangle your rope, or you try to put your girder down into past r equal 2gm, is it'll be torn apart. And no physical thing could exert enough force to hold you at rest there. Okay? Yeah, so, but yes, you can do these kinds of calculations. Anything else? Okay? So, and if we, a different way, we saw the Kruskal-Saccharis coordinate system. We can talk about And Eric was talking about that yesterday. So in this coordinate system, let's just think about this quickly. What's the time coordinate in this coordinate system? Just read it. Which one? V is the time coordinate. Is it always a time coordinate for all values of r? Yes, and down to r equals 0. And Eric described what kind of a world line does a particle at fixed r follow in UV coordinates. So I'm saying that this is fixed. What kind of a thing am I talking about there? Yeah, it's equation of a hyperbola. And so on Eric's graphs that he was drawing, you saw the lines of constant r as hyperbolas, and so on. And so the r, this function now, as he described, this is no longer a coordinate. We're not treating it as a coordinate. We're treating it as a function that depends on these coordinates, but it's still the circumferential radius because the metric says so. And you can read that right off of this part of the metric. All right? We good? Okay. So let's do a different thing. There's another way to solve difficult equations, and that is make approximations. And what's really nasty about the Einstein equation is that it's nonlinear. So let's make it linear by perturbing the metric around flat space. And now we're going to assume nearly Cartesian coordinates that I'm going to call t and x and y and z. They are not Cartesian coordinates. Do not make that error. They are nearly Cartesian coordinates, and we'll run into trouble if we assume that they exactly are. But you do a kind of a dance here. You do a lot of intuition based on your knowledge of Cartesian coordinates, but you've got to keep in the back of your mind that these are not really Cartesian coordinates. You've got to be careful. And I'm going to say that the metric is the flat space metric plus a little perturbation. And that perturbation has got to be symmetric because the metric is symmetric, but I'm going to assume it's a lot less than 1. So it's a tiny perturbation compared to the, yeah.
Okay, so the question that it always brings to me when I see this approximation, it's
Uh-huh.
I have the feeling of what is to say the modulus is smaller than 1.
Uh-huh.
What is the modulus of a tensor?
No, what I mean is the, yeah.
Okay, but how can you say that it's small? It's component by component? How?
Yes, component by component. That's exactly what I mean. Each component is small compared to 1. Okay, so I'm not taking the modulus of the tensor as a whole. I'm taking each component. I want each and every one of those components to be small so that I can neglect. Ultimately, what I'm going to do is drop powers of the component size squared. So I want each individual component to be 0, or to be small. Okay? Now, I can find out what the inverse metric is. I might think, oh, the inverse metric is just the inverse eta flat space metric plus the h mu nu with raised indices, but that turns out to be not correct. And I'm defining this thing with raised indices. I'm raising them with the flat space metric rather than with the full metric. Why? What if I put g mu nu here? Yeah, I get higher order terms, but I'm neglecting terms of order h squared. So it doesn't matter. I'm going to raise with the flat space metric. Okay? So, but I could take that as a definition if you like. And so what I want this to be is the Kronecker delta. I want it to be I want this to be the genuine inverse of that. And so I do a calculation here. Here I've got these terms, and I multiply them all out. And I've got a term here that involves h squared, so I'm going to drop that. And I write various things and raise indices, and you can follow the calculation, I think, if you sit down with it. But basically, you end up with, if you have that minus sign here, you end up with two terms of first order in h that cancel, and you get the you just get the Kronecker delta, which is what you wanted. So, but this is important to have in mind, that when you've got the upstairs, the metric with upstairs indices, you want to subtract the perturbation, not add it. That's the main point. Okay? So, because we're dropping second order terms, like I say, if you want to raise an index, fine, but it's just the same thing as raising it with the ordinary metric, because I'm dropping terms of h squared order. I'm sorry? No, any arbitrary tensor. You just, oh, well, sorry. Got to decide what order the tensor is. And it turns out, let's hold that question, because there is it turns out that you can still do it with almost any tensor you care about. But yeah, technically you got to make sure what the order is. So let's look at the Christoffel symbols. Why does the Christoffel symbol become this simpler expression in this limit? First of all, I replace the upstairs metric with the flat space metric. Why?
You were using the metric to
Yeah.
upper index there, so you can.
Yeah. These terms are all of order of h, so I'm dropping h squared terms. Okay? And why do I only have h's here? Yeah, the flat space metric doesn't depend on anything. So the Riemann tensor in this approximation becomes this, right? Does that make some sense? Yeah, it's just like it was in locally inertial frame, except that we remember that only the h parts vary. So you can use the same mnemonic there that you would use in locally inertial frame. And the Einstein equation becomes this, okay? And the Ricci tensor then becomes this, which is just taking the Riemann tensor and summing over the two indices that you need to sum over. And now I want you to notice that the Ricci tensor is of order h, right? And so the stress energy tensor is of order h. So when I raise and lower indices on the Ricci tensor or the stress energy tensor, I can use the flat space metric because I'm neglecting only terms of order h squared. Does that make sense? So here's the answer to the question you were talking about. With the Ricci tensor is of order h, the stress energy tensor is of order h, so we can raise and lower indices with the flat space metric of those things too consistently. Okay? So, now, my Einstein equation is still not very simple. I've got 4 terms here and it's equal to this complicated thing. Yuck. Okay? But we can make things a little easier, and this is not going to be an obvious thing. But let's define a capital H where I take h, the perturbation h, and subtract off half its trace. Okay? So the trace the trace is just sort of the diagonal elements summed. Of course, you take the t component is negative. But this is what we mean by the trace in flat space-time. And this is called the trace reversed perturbation, because if you actually calculate the trace of it, it turns out to be negative the trace of the other, of the original perturbation. So this is sort of the same perturbation, but negative the trace. All right? And so you can go backwards. If you know the capital H's, you can go to the small h's. That's pretty straightforward. Then the Ricci tensor, and I'm going to define this. This is the D'Alembertian box squared. Is just the double derivative, the double partial derivative summed over the flat space metrics. So it's minus double derivative with respect to time and plus double derivatives with respect to the spatial components. You're familiar with that operator. Okay? And so I plug in what the Ricci tensor is, and I'm going to drop higher order terms, and these terms cancel. And so this becomes what the Ricci tensor is. So my Einstein equation becomes this. Yes? Yeah. Yeah. Yeah, yeah, I think there is, and you're pointing out a really interesting thing. Yeah, we're seeing this pattern over and over and over, and I think it's expressing something deep in the mathematics. Certainly, the part where you're talking about the Ricci or the Einstein tensor from the Ricci tensor, that is expressing something very deep in geometric. If you use the mathematics of Cartan, that emerges naturally in that mathematics. So what this is suggesting is that our mathematics is kind of crummy for doing these calculations, that if we use a slightly different way of formulating the mathematics, all these terms would come out automatically, and they'd be buried inside. But we're using sort of stupid mathematics, and so we still have complicated terms. No, this is I've left it as little h. I think that emerged. Yeah, it's emerging as I'm following through from here and here and here. Yeah, I'm deliberately doing this. Later, I'll rewrite the whole equation in terms of capital H, but right now I've got the little h. Okay. Now it turns out though that we have coordinate freedom. So here's my Einstein equation again, and it turns out that I have coordinate freedom to set these capital H's equal to 0. And I'm going to talk about that more later, but right now let's just accept that and see where it takes us. So if I can set, no, I'm sorry, I'm not setting the capital H is equal to 0. I'm setting the divergence of the capital H is equal to 0. Because the divergence appears here and it appears here, and if I can set that divergence equal to 0, then the Einstein equation becomes this simple thing. So now I can make the Einstein equation, this complicated equation, equivalent to solving simultaneously these two much simpler equations. All right? And the beauty of that is we know how to solve this equation, because we do it all the time in electricity and magnetism. So let's just think of solving this equation. We know how to solve this equation in electricity and magnetism. We it's simply you take the potential of a point particle and you sum up over all the particles in your system and do an integral over of all the point particles in your system. And then the only thing for adding the time derivative is that you've got to do that at a retarded time, so your potential out at a distance reflects the arrangement of particles at the earlier time, light travel time ago. All right? So we know, the point is, from electricity and magnetism, we know how to solve this equation. And it's a linear differential equation, so you can write lots of proofs and things like that about what's possible in ways that you can't for nonlinear equations. So by deleting all the h squared terms, we've made a huge simplification. So the solution is the h mu nu at a distant point r and at a time t turns out to be, just by doing a sort of a comparison, 4g times the stress energy bar, where I'm simplifying the complicated expression. I'm evaluating that at t minus s, where s is my distance in meters, and I'm measuring time in meters, and I'm going to integrate over the source. You know, it's our little r coordinate is inside the source, and I'm integrating over all those little r's. And that's the answer. Okay? So for example, let's consider a static spherical star with total mass m. Assume that the pressure is negligible, so that the only non-zero stress energy component is the time component, which is rho, the energy density. And so then, first of all, the first step is to figure out what this t bar is. Well, I know what the only non-zero component of this is rho, tt, the tt component is rho, and all the other components are zero, but what's the trace? Well, the trace is going to involve rho also, and you can work it out, and it's just, you get all four of those diagonal components is 1/2 rho. So that's not too bad. And then you know from electrostatics that the potential energy outside the spherical source is same for that is a particle with the same charge located at the sphere's center. So find all the components of h mu nu at a point outside the star that's a distance r from the star's center. Well, how would we do that? So I'm saying that let's take htt for example, is equal to simply, I'm going to treat it as one big charge at the center. So I've got 4g, and I'm integrating 1/2 rho over the volume. Well, that's going to be 1/2 the total mass. And I'm going to say at a distance s, say from the origin. And it's static, so I'm not going to worry about the times. And so this is going to be 2gm over r, or s, I'm saying here. Okay, and what about the xx component? Same thing. Y component, same thing. So what's my metric now? My metric is equal to, so each of these are positive. So my metric is going to be -1 minus 2gm over, let's change s to r, dt squared plus, and then I've got plus 2gm over r times dx squared plus dy squared plus dz squared. That's my solution. That's even easier. And do you recognize some parts of that solution? First of all, why have I got the minus sign here? I could have written it as minus 1 plus 2 gm over r because the perturbation is plus. And then I'm adding it to the flat space metric, and I'm adding it here, the flat space metric here. Okay? This is just the Schwarzschild. Yes, it's a linear approximation because the r is not the same as, yes, you're absolutely right. And this is a linear approximation to 1 over 1 minus 2 gm over r if you do binomial expansion and drop higher order terms. So yeah, this is the linear approximation to the Schwarzschild solution. And that's a powerful statement. It's even easier to get at. And we could calculate h mu nu, and it's important to check that we have that condition correct, and it is. So, yeah. Because the 1/2 rho. So I'm integrating over all that, I get 1/2 m. Okay? Yeah. Uh-huh. Yeah. Yes. Yep. Yeah. Uh-huh. Right. Yep. That's right. And so, just to unpack that a little bit, he's first of all talking about that what we really ought to do if we were doing it near the Earth, which this calculation would totally apply. But the Earth is rotating, so we're not. The off-diagonal terms are not all zero. There are some time-space terms that are significantly not zero, and you'd want to include those in the calculation, and then you get a cross term in the metric that comes out of that, and it approximates the Kerr metric near the Earth. And then, but why don't we use that as a background instead of the flat space background when we're talking about gravitational waves being detected at Earth? And the answer is, well, the gravitational waves are of order h. And the correction terms here are of order h. So if I kept the correction terms in, then I have terms of order h squared, and 10 to the minus 21 squared is really, really small. Yeah, it's just totally negligible. Exactly, that's the point in this approximation. So if you had a really strongly rotating source where these were not negligibly small, then you would worry about it. But the Earth is not such a source. Okay? Now I want to show you something that's really cool about the linear approximation, the weak field approximation. I can define a gravitoelectric and gravitovector potentials. I'm just going to define those. And then, stop it. And then our coordinate condition, which was the divergence of capital H equals 0, our coordinate condition implies this. Do you recognize that equation? You might recognize it as being the same thing as that. Do you recognize that equation? That is the Lorentz condition, the Lorentz gauge condition for electromagnetic waves. Okay? By the way, not a misspelling. This is not Lorentz with a T. This is not Enrique Lorentz, but a different Lorentz altogether. And a lot of textbooks get this wrong, and my first edition got it wrong. And somebody pointed out that this is Lorentz with just the Z. All right, but anyway. All right, so now I'm going to define a gravitoelectric field the same way that I would in electricity and magnetism. I'm just going to define that thing. And then I'm going to say, well, gee, what's the divergence of that thing? So I plug in and take the divergence. So this is just the what is the term for that? And then I do the same thing here, and that's this the D'Alembertian of the gravitational potential. And so I plug that in, and I know what these are. But by the weak field Einstein equation, so I plug in what HTT and HX, and each one of these things, it has a T component. I've got the 1/8 here, so I had 16 pi, and now it's just 2 pi. And then I've got 1/2 times the trace for each one of those. And I add all that up, and look what I get. Now, does that equation look familiar to you? Okay. It looks almost like Gauss's law for the electromagnetic field, except what? Minus sign. Why do I have a minus sign here? Well, in electricity and magnetism, like charges repel each other, but in gravitation, like charges attract each other, so I've got to have the minus sign. Okay? So, I can define a magnetic field. And the magnetic field, and then I just do some vector stuff with that, and I'm going to add and subtract a term like this so I can get the square, the D'Alembertian squared there. And then I'm going to plug in what that is in terms of this, the actual perturbation. But this is one of those equations by the Einstein equation. That's going to be this, which now I'm thinking about, I'm actually got sources where energy is flowing. And so some of these off-diagonal terms would be 0. In fact, this is basically, I'm going to call that the current, a mass current density. And then, so it's energy flux. Actually, be a better way to say it. It's energy flux in the 3 spatial directions. And so, does that equation look familiar then? Yeah, that's just the Ampere-Maxwell relationship. Okay? And the way we've defined the potentials means that the other 2 equations, the fact that the divergence of the magnetic field is 0 and the Faraday's law, just emerge from the fact that I can write these fields in terms of potentials. So it's just the same thing. So hey, look at that. I've got Maxwell's equations. So in the weak field limit, the gravitational field behaves just like electricity and magnetism, except with the minus signs. So you got to remember the minus signs, but other than that, you're fine. And you ought to be able to predict everything using these equations instead, and using your intuition about those equations that you've developed by long and hard effort. Now you can make it pay off here. So, note the minus signs. Gravity is attractive for like masses, and we need to use a left-hand rule for magnetic fields where you'd use a right-hand rule normally. Okay? So in terms of saying if I've got a mass current or an energy current going around, like I have a rotating star, instead of using my right hand to figure out the direction of the magnetic field, I use the left hand. Okay? Vengeance for all us left-handers. Finally, it works. Okay? So, this applies quite generally for weak fields. In other words, this part applies quite generally for weak fields. Of course, this is all useless because I'm just defining fields. I can define fields any way I like. This is all useless unless you have something like this, which says that this is the way you interpret the physics of the fields. They're causing accelerations with respect to your coordinate system that are like the Lorentz force law. Now, the conditions that this applies are much more limited than these. This only requires that the field be weak. But this requires the time derivatives be small, that your source is not moving, whatever particles in your source are not moving very fast compared to the speed of light, things like that. So, and you'll also note the factor 4 here. That's just the difference between gravity and electricity and magnetism. That magnetic field, as I've defined it, counts 4 times as much. Okay? But this means that all your electricity and magnetism intuition works. You can now talk about what happens to particles near rotating objects. And so, for example, use the gravitomagnetic analogy to argue that a particle falling initially radially in the equatorial plane of a spinning object experiences an acceleration component that deflects it. Okay, frame dragging, in other words, right? So let's think about that. Here I've got a star. It's rotating this way. What kind of magnetic field does it create? Gravitomagnetic field does it create? Yeah, you need to use your left-hand rule. So the magnetic field is going into the board there, which means it's coming out of the board around the star, right? So now let's have a particle that's falling inward. And I'm saying, okay, here's my velocity. Here's my field that's coming out of the board. But it's attractive. So it goes that way. Did I do that right? Let's see. Yep. So I'm going this way. Field is coming out. Particles falling in. Field is coming out. Yeah. Oh, sorry. I'm using my left hand. That's why. Yeah, there we go. There we go. Yeah. So no, I don't need to worry about the attractive part of the mass there because that earlier law, it just works in the normal way that you'd expect it to work. So my field, I use my right hand for this. Velocity is this way. Field is into the board, or out of the board. My force is downward, deflected in the direction of rotation. Yes. Yeah. Yeah. Yes, if you had a magnetic monopole. Yeah, yeah. Yes, in other words, you're asking, I could have a non-zero thing here if I had magnetic monopoles, and what would that look like for gravitation? Well, the way I've defined the potentials, that's impossible. Yeah, and so I don't know if a more general theory I could define the potentials in a little differently and get a source term there. I don't know. I haven't explored that. Yeah. Uh-huh. Yeah. Yeah. So it's expressing the Bianchi identity. This is expressing the Bianchi identity. Yeah, yeah. Source. Yeah, right. Yeah, yeah. Okay, but the way the formalism is constructed at this point, you can't have it. Okay, yeah. Right, right. Yeah. This is part of the beauty of this is basically what we're doing is we're considering the perturbation field to be a field on top of flat space-time, and we're working in the flat space-time background. And we get to do that because any corrections to that scheme would be of second order, and we're ignoring those. And so this is a very powerful way of looking at the at general relativity in the weak field limit. But it only works if you can really neglect those second order terms. And like I say, this is the difficult part. And it's particularly difficult because even in the weak field limit, if you have a relativistic source, you're not going to have this obeyed anymore. And then the fields don't mean what you think they mean. And your electromagnetic analogy falls apart. But this is good for intuition, even like working with Kerr black holes. This is still gives you qualitatively what's going on. So in fact, one of the paradoxes of the Kerr black hole is that if you have a circular orbit around a Kerr black hole, you'd think by sort of a frame dragging analogy that it would orbit faster as it goes this way than it goes this way, but it's just the reverse. It orbits slower this way and faster this way. And you can totally explain that with a gravitomagnetic analogy, whereas you can't, the frame dragging thing misleads you. So this is a very, very powerful technique. Yeah. Yes, yes, that's right. So if you went from south, so if you were coming upward, I see your question, the nature of your question. So yeah, the gravitomagnetic analogy would say no at the point where you're crossing the equator, but then you begin to cross field lines as you go above or below the equator, and you'll get some bending. But at the equator, no, there would be no force. He was, yeah, sorry, yeah, let me restate the question. He was asking, so if I have a particle that's coming out of the blackboard here, what would be the frame dragging effect on that? And the answer is you could resolve it using the gravitomagnetic analogy by saying I'm going parallel to the field line at that point, so I should experience no acceleration. And I think that's right in the full Kerr solution too. So the frame dragging analogy is just a misleading analogy. You're not really dragging the fabric of space-time around the star. It's different than that. And the gravitomagnetic analogy helps you with that much more than the frame dragging analogy would help you. The frame dragging analogy works for this, but it doesn't work very well for other things. And that's really important to keep in mind. Of course, you really should solve carefully for the Kerr metric because I'm using weak field intuition and that's not necessarily going to work. Yeah.
Could you also look at it as having higher angular momentum in order to maintain a circular orbit around a black hole going out?
Yes, that's part of the idea. Yes, yeah, that's exactly right. And so, yeah.
Can this formalism help us into calculating, or at least can give us an idea of the amount of energy carried by the gravitational waves? That is, can I define something like the Poynting vector for these gravity-magnetic fields?
Yeah, and the short answer is no. Yeah, yeah. So the analogy goes only so far, and this is not a particularly good analogy for electromagnetic, for gravitational waves. So even though this all applies in the weak field limit, what doesn't work is this in the case of gravitational waves, because you have significant time derivatives, and you can't ignore the time derivatives, and the time derivatives give you a bunch of extra terms there, and it just doesn't work. Plus the fact that we're still not in really Cartesian coordinates, and so the wiggle with gravitational waves, you have to decide if the wiggle is the wiggle in the coordinate or is the wiggle in the actual space-time. And in order to do that, we just can't do that in this formalism. And so it's not good for gravitational waves, and that's too bad, because it really would be nice if it would. Okay? But for static or stationary situations, this can be a very powerful technique. You can solve inside the star, outside the star. Very easy to do this. And so a very good, useful technique for solving the Einstein equation. Okay, anything else before I go on? Okay, so I want to talk a little bit about gauge freedom. I said we could require it that this be true. Why can we do that? Our nearly Cartesian coordinates are not actually completely defined. There are lots of coordinate systems that satisfy this restriction. I can wiggle my coordinate systems. I can cause them to bend a little bit. And so, in fact, I have a set of coordinate transformations. I can go to new coordinates where I'm tweaking my old nearly Cartesian coordinates by a small function. Small meaning every component is small. I'm just going to tweak them a little bit, and I've still got nearly Cartesian coordinates. I'm not going to change the metric very much when I do this. And so if I'm going to do transformation partials, I try and figure out what these derivatives are, and I'm taking the derivatives with respect to the new coordinate, but the derivatives with respect to the new coordinate. So I'm working out what this is, and but the derivatives with respect to the new coordinate are basically, well, I've got this is just the identity coming from that. I've got the derivative left over here, and then I'm going to re-express this in terms of ordinary or derivatives of the first coordinate system, just using standard partial differential calculus. And then if I think about what that's going to be, I've already written what this is to first order, so I'm just plugging that in again, and I'm dropping higher order terms, and you end up with, in the first coordinate system, you have a derivative of this function that I'm using to transform the coordinates time. And this is going to be small, so it's mostly the identity operator, but it's going to include a small change. So our transform metric, I just write what the definition is in terms of the ordinary tensor transformation law. I now put in what that, I've figured out what these derivatives are, and here's what the metric it was in the original coordinate system. I write all that out and think about doing these sums over the Kronecker deltas, and I end up with I've got still the flat space metric. I've got these two perturbation terms from the coordinate transformation, and I've got the h mu nu. So the h mu nu prime is just the old h mu nu plus a symmetric version of the derivatives of the transformation functions. Okay, so far? So substitute this into the Riemann tensor and grind it all out. And basically I can replace these prime derivatives by testing. All right. So I can replace the prime derivatives by the n prime derivatives. Why? Yeah, the only difference between them is higher order. So I've already got order h there. I'm not gonna keep higher order terms. So the bottom line is that the primed version of the Riemann tensor is the same as the n-prime version. So doing this little coordinate tweak doesn't even change the Riemann tensor. Which means that if I have a solution to the Einstein equation before, doing this little tweak won't change the fact that it still satisfies the Einstein equation, which is built out of the Riemann tensor. So I can do this little coordinate tweak and I've still got a solution. That's great. Okay, so this is analogous to gauge transformations in electromagnetic theory, where I can add a gradient of a scalar field, or I can add the time derivative of the scalar field to the electrostatic potential, and Lorentz gauge is equivalent to that expression. And so this is Lorentz gauge in general relativity. I have that freedom to choose that. But does the transformation really give us the freedom to do that? And the answer is, well, let's find out what so we knew what the transformation of the basic thing is. I'm going to figure out what the transformation of the trace is here. And that's just the trace minus this correction term. And so now I'm going to figure out what the transformation of the capital H is. And here is the result. And so what I want to do is I want to make this 0 in my new coordinate system. So I'm going to force this to be 0 in the new coordinate system, but here is the transformation of that, and I'm taking a lower derivative there. And these two terms end up canceling out when I do that. So in order to make that work, this is just the box, the D'Alembert squared. So in order to make this work, all I have to do is solve this equation. This is my original divergence, which is presumably not 0. And all I have to do is solve this equation. Well, can we solve that equation? And I hope you mostly know that the answer is yes, we can always solve that equation. That's an ordinary second-order differential equation, and mathematicians have established that under reasonable conditions for the driving functions here, you can always come up with a solution to that. And then you've got a particular perturbation that has taken your original capital H, whatever it was, and mapped it to a new capital H that still solves the Einstein equation, but now the divergence is 0. So what this amounts to is choosing coordinates in a way that I satisfy the Lorentz condition, which makes the Einstein equation simpler and easier to solve. So I just need to be assured that we can always do this, and then what we're going to do is since we know we could always do it, we're just going to impose the condition right away at the beginning and only accept solutions that satisfy that, and it'll make the Einstein equation easier to solve. Yeah. Yeah. Uh-huh. Yep. Uh-huh. Yeah. 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 If you have a solution already, if you have a capital H or a small h that solves the Einstein equation already, then doing this little coordinate transformation will not change that fact. It still solves the Einstein equation. Okay? And that's the beauty of it. Okay? So we're going to make, but we still, in fact, we've got a family of solutions. So what I want to do is find a solution of this form, but we have families of solutions because if one function f is a solution to that equation, then I can add any constant times f0, where f0 solves the homogeneous version of that equation. And mathematicians are telling us that's what the general solution looks like. And so I still have, even after I've done this, after I've applied the Lorentz gauge, I still have some freedom left because I can add any new solution of this, and I'll still not only solve the Einstein equation, but I'll solve the Lorentz gauge too, and yet it's a new solution. So I still have coordinate freedom after this. It's more limited. It's got to be solutions of this kind of function, but I still have coordinate freedom. And that is going to be crucial to us as we go on to gravitational waves, is taking advantage of that extra degree of freedom. Okay? So the very last thing that I want to say is to answer the question you were raising about, is that really little h here? Yeah, it'd be real nice if I could rewrite the Einstein equation to involve big H, so I'm only worrying about big H. So let's do that. So here I'm trying to solve the Einstein equation with this Lorentz condition. So I'm going to contract the Einstein equation over the three indices to sort of find the trace of the Einstein equation, and I get this result, where this is the trace of the stress energy tensor. And then I plug that, so I want to subtract this from both sides of the Einstein equation so that instead of the D'Alembertian of little h, I have the D'Alembertian of big H. So I'm going to subtract half of this from both sides times the metric tensor. 1/2 times the metric tensor times the little h. And then by using this equation, I'm essentially subtracting off that last term. So I get 16 pi g times just the stress energy tensor. So this is really the value of using the big H's, is that it makes the equation even simpler by making the right-hand side simpler. And I can always, once I've got a big H solution, I can always go back to the little h by subtracting half of the trace. Okay? So, very nice pair of equations then. This is the Einstein equation. This is the Lorentz condition. Still have some gauge freedom left over to choose my coordinates. That's where we're going to go with gravitational waves. And we'll do that, I guess, on Tuesday. So, that's it. So, any questions that you have? All right. right, very good. Thank you for your attention.